I should do the tradition, shouldn't I? Hello, I'm David. I'm the coordinator of the Maths Learning Centre. It's Semester 2, 2018, and this is a revision seminar for Engineering Maths IIB. A course which I never did myself. I seem to remember doing multivariable calculus at some point in my life, but it's pretty hazy the first time I did it. So as with most things in second year, everything I know about this I have learned by helping students in the Maths Learning Centre. So I tend to only know things that people are worried about. So it gives me a fairly skewed picture of what's going on. So feel free to correct me or ask questions or tell me I'm doing something wrong at any point. That's important, especially if I do something wrong. You don't want that to labour on for half an hour when I did lost a minus halfway at the beginning and you noticed it and didn't tell me. That's ridiculous. So it won't be exactly the sort of thing that would happen in your exam, because in your exam you won't have a crowd of about 40 people watching you to see if you're getting it wrong, which is sad. I wish we could all have that, but you don't. So I'm going to try and give you the ways of thinking about things, and anyway, you can hopefully learn something from me. So I've had like 1 or 2 requests which between them cover basically everything in the course, so that's just not going to happen. Still trying to decide what I want to do. I was asked to talk about parameterizing things and to talk about doing path integrals around closed curves in the complex plane. Yeah. And I was also asked to talk about doing partial differential equations with Laplace transforms. So we'll give it a go. I should have brought a textbook down. That would have been helpful as well. So the resource that I have, and the only resource I have right now, is this sample exam. And I know there are solutions to it, but it's the only thing I have. So if you have questions other than this that you don't have solutions to, or that you prefer me to do, please let me know. But at the moment I'm going to just start with this, if that's okay. So this is, we need more zoom. This is the practice exam, or it will be, that was given out this year. Which I have to say, having scanned through it, is rather interesting. Asked some questions backwards that we would normally expect forwards. It's rather bizarre. So that tells you a little bit about the mind of your lecturer. Okay, so I'm going to start here and see what happens. When I put it on the website, I usually try and put them in under the headings of whatever they're for, but I will just put this all in one at the bottom so you can find it, but I'll try and split it up as well so you can find whatever you need. So let's read it. Use the Laplace transform method to solve the partial differential equation du on dx, curly du on dx plus curly du on dt plus u is 0, where 0 is less than or equal to x, which is less than infinity, 0 is less than or equal to t, which is less than infinity, subject to u of x and 0 is 0, and u of 0 and t is t e to the minus t squared. All right. Rightio. Let's see. It might be useful to have a look at the back here where there's some stuff about Laplace transforms. This looks useful. Laplace transforms about derivatives. That looks like useful because I've got derivatives here. And I have a feeling that I want to do the Laplace transform with respect to one of these variables. I wonder which one it should be. I really don't know. I haven't looked at this yet. So all of these words I'm saying are my exact thoughts. I am not pretending. Sometimes I'm pretending when I say I'm not pretending, but I actually am pretending. So, no, not pretending. Now you'll never know. Okay, I'm going to need to choose which one. presumably whichever one turns into something I can deal with. So actually, just let me see if I can make a decision. When I do this Laplace transform here of a derivative, the Laplace transform of the derivative of something, s times the Laplace transform of the original minus f of 0. So I would need to know what, if I Laplace transform with just one of these variables, with like x or t, I would need to know that when I sub that variable in for 0, that it comes out to something as simple as it can possibly be. That would be this one. If I sub in t equals 0 into u, I get 0 no matter what x is. And so if I Laplace transform with the t and it's still got an x in it, then it will come out to something that I have an answer for. That's the one I want to do. I want to do the Laplace transform with respect to t, which seems reasonable because all of these say t and s anyway. But just checking, you never know. It could have been the other one. You never know what sort of things are going to do. With respect to t, and tradition, I suppose the u would become a capital U, I guess. And so that will be a function of x and s. Okay. So du on, damn it, where's my real eraser? So the Laplace transform of du on dt should be, according to this, s times the Laplace transform of u minus u when t is 0. Okay, which is s times capital U minus 0. Okay, and the Laplace transform of du on dx, I guess, is just going to be d capital U on dx. Okay. Sure. And is that everything? What else have we got? Oh, u. Well, and the Laplace transform of just u is capital U. Okay. So my equation is now, it was du on dx, which becomes a curly d capital U on dx. And then we had du on dt, which was s of u. And then u became just capital U. And that would still be 0 because the Laplace transform of 0 is 0. Excellent. I think I've done the Laplace transform correctly. My writing's really big. I would really suffer in exams where you have to write on the page. I'd have to learn to write smaller, I reckon. Oh, just a second. We should change these information here. Just a second. So we know that... No, we'll come back to that. So this we can do. So as far as I know, we can rearrange that we can attempt to solve that differential equation in terms of x, I think. That seems like a reasonable thing to do. Yeah, let's do that. Maybe the moral of this story will be how you can pass with only vague memories of what's in the course. That'd be a nice thing to learn. Okay, so it's sort of like, it's separable, isn't it? So you have like a 1 on, sure, okay, let's give that a go. 1 on u I'm really making this up. Please tell me if I'm doing something bizarre. I didn't even bring the solutions because do we need to put a plus c in? Is that important?
Yes.
Okay.
The c is also with respect to...
It would be a function of s.
Yeah.
Okay. I shouldn't call it c then, because that's confusing. A constant, which is a function of s. Let us call it f. We don't already have an f? No. Okay. All right. Yes, that makes sense because it's not really a du. It's a partial derivative. Okay. Okay. That doesn't look fun. I suppose I could replace that entire e to the fs with just another function g of s or something. How do we figure out what that is? I suppose normally when you're trying to figure out what a constant is, you sub in one of the values of the... Yeah, you'd sub in what happens when x is 0. And that would normally tell you what the constant is. Okay. I don't know. Maybe we should have done it back there. Okay. So we know that u0t, well, we know that u of 0t was t e to the minus t squared. So capital U of 0s would be the Laplace transform of that, I guess. Oh crap, how do I do Laplace transforms of that? That's what I'm looking for. Sorry? That's what I'm looking for. The x squared distresses me.
Do we need to know it as a Laplace transform?
Oh, because we're going to just put it back again later? Because we're going to untransform it anyway?
Yeah.
Sure. That's fun. Okay, so we can just say capital U of 0s in this spot here. Yeah, that's awesome. So capital U of 0s like that. So I just, oh crap. You get to see, I'm going to do what I wanted to do before and just call this g of x s, because that's fine. Okay, so let's just see this. Capital U of 0s is e to the minus s minus 1 times 0 times g of s. And so therefore this g of s is capital U of 0s, because that's 1. Right. So U is actually equal to that. Good. So presumably we would untransform this and get back to what we were hoping for. Let's do that. All right. So the U will be the inverse Laplace transform of capital U, which would be, all right. Now that's a thing. So if I Laplace transform this U0s, that would just be little u of 0t, if I inverse Laplace transform that. And when I multiply something by an e to the power of something first, and then inverse Laplace transform that, there's a rule for that on the table. There's a shifting thing, right? That one? Yep, so if I go backwards from here, I'll get to there. Sweet. So we have, oh crap, we don't have that. We're going to have to just do some work. Sorry about that. Because what we need to do is we need to have e to the something times s. And we don't have that, so we're just going to have to do a little bit of work. Right, that's better. So now it's an e to the minus x. That's just... It's already a minus, isn't it? Doesn't matter. Ignore that. All right. So that e to the minus x counts as a constant because when we do our Laplace transform, the x's will stay exactly as they are. So I can bring that out the front. And then when I do my second shifting theorem, e to the minus a s f of s becomes little f of t minus a, little u of t minus a, and that little u, oh crap, we've already got a u, but that's okay. This is the other u. Okay. So this will become the function that we were transforming, and instead of a t, I'll have a t minus a, and the a is x because that's the thing multiplied by the s, and then this thing. I will call it h for heavy side, just so I don't get it confused with the other thing. Okay. What does that mean? I have a feeling that's supposed to go away somehow. Ah, so you're saying that if I go all the way back to here, that the u of 0t is t e to the minus t squared, and so the u of 0 t minus x will have a t minus x in both of those positions. Okay, so u of 0t is t of e to the minus t squared, so therefore u of 0 t minus x will be t minus x e to the minus t minus x squared, and so therefore my u of xt is now e to the minus x t minus x e to the minus t minus x squared times my heaviside function of t minus x. I just call it h for heaviside here so that I didn't get it confused with that u, but now that that u's gone, I can just call it back the u that it used to be. Sorry? Oh yeah, the squared is not there, is it? It's here. Right. There we go. Cool. What does that even mean? I mean, I'm supposing that we've got an e to the power of crap, with negative crap, so it'll get smaller and smaller as x gets bigger. But it's also multiplied by t minus x, so that's how far the x is from the current time, I suppose. So it still gets smaller when x gets bigger. When t gets bigger, I suppose it'll get, this bit gets bigger. And it only turns on when the time is bigger than the current x position, whatever that means. Because this u is 1 when this number's positive, so as long as the time is further than the x, whatever the units they're measured in, as long as the t is bigger than the x, that's when the function turns on. And it's only equal to this when t is bigger than x. Okay. Which is sort of cool, because this bit here will make it equal to 0 when t is equal to x, so it seems like it's going to sort of, if I've got a specific x, then it's going to do this, and then it's going to start something like that, I'd say. That's my guess. Not that that's important for solving the problem, I just wanted to have a feel for what was happening there.
One of our previous exams, the focus actually had give a qualitative explanation to solve the...
So if I was going to attempt to give a qualitative explanation, it would be the only thing I'm absolutely sure of is when x is large, this is close to 0. Yeah. And also when t is large, it's close to 0 as well because of this thing here. So it does have to taper off for both at the end of space and the end of time as to get smaller there. Rightio. Okay, let me just go back and see what happened, because I was figuring that out basically from scratch, not having seen any examples of doing this before, or possibly maybe a year ago, the last time I saw this. So what happened? I did the Laplace I figured out that I had to do it with respect to t, because when t was 0, it came out to a number. That was useful. And then after I made that decision, so that was the first thing I did, I made the decision. And then I did the Laplace transform in terms with respect to t. So that was all of this bit here, that was doing the Laplace transform. And what that managed to produce is a differential equation still. And so then I did that differential equation, which is this bit here. And then I subbed in the other initial well, I didn't really do anything. I just subbed in a condition and I left it as it was. So I subbed it in and figured out what this function was in terms of the original u. That's what I did. And then I did the inverse Laplace transform. And then I used the last condition. Okay, those were the bits that I did. I should write labels on those. So I decided which variable to do the Laplace transform. That's what I did there. And then I did the Laplace transform. And then I solved the DE that resulted. And this is still part of solving the DE, but I wrote the missing bit in terms of u. And then I did the inverse. And then I subbed in the last condition. Well, it seems like not the worst plan. I've used everything that I was given in the question, so I reckon I've probably done it right. Comments? If you've got any? Thumbs up from at least one person. All right. I will take that as a win. Okay. Unfortunately, it took me 3 pages instead of the 2 that they provided in the exam, so I'd probably need to write smaller. Or just, they do give me a couple of pages at the back, so I'll have to use some extremely clever labelling to say where everything went and where everything came from. Oh, for the days when you used to just be given a book of paper and you could take as much space as you wanted. Okay. Now, this is for you, not for me, so please, if you do have something to ask, ask away, and it can be as stupid as you like or as clever as you like. All kinds of questions are valid here. Yep?
Yeah, so my question is about, not actually about the past transform, so I might ask it later.
Okay.
The question 3 part E is where...
In this exam? All right. So let me have a quick look, and then I may say, get back to me and remind me. Nope, not there yet. This thing here? All right. Well, this question 3 part E has at least one parameterization in it, so it wouldn't be the worst thing to talk about because it would at least cover that in small aspects. So why don't I just start there and see what happens. And if this turns out to be me talking through the ideas that you had to think in order to produce the solutions, then I hope you don't mind. Okay. The velocity... Oh, I need to go back in again. Question 3. The velocity potential of a flow is this. Oh, quick eagle piggle, catch Macapacas ogpog. Honestly, it doesn't make any sense. So I'm given to understand that when you say thing potential, the gradient of it is the thing. So if I say velocity potential and I calculate the gradient of it, it will give me a velocity. And so if I had electrical potential, then when I differentiated it would give me like an electrical force. And yeah, so that's what I'm thinking. And when they say flow, I'm presuming that there's like water or particles of some sort moving, and at any point the speed that they're going at is calculated from the coordinates of the current point. Okay, and presumably that potential means that they'll flow, I think, sadly, towards positive potential, which is opposite to the way gravity works, but whatever. Okay, I just need to talk these things out so I don't get freaked out by the words. Okay, so even before they've even asked me what to do, I'm expecting that I should differentiate that at some point. And the first question says, find the velocity vector of this flow, which is bold V, which is the gradient of F. Okay, I can do that. So I differentiate that number in all three directions and put it in a vector, and that's the vector that I want. So I have df on dx would be 2x, df on dy would be 2y, and df on dz would be 1. Okay, so that's my velocity vector. So at every point in space in 3D by the look of it, so maybe it's an airflow, every point in space in 3D, if I look at the coordinates of that point and it's x, y, z, then I can find what the velocity at that point is by doing 2x and 2y and 1. Okay, so it doesn't matter what height it is, the velocity is always in the same direction. That's kind of cool. And if I'm at the point 1, 2, the velocity would be 2, 4. So the velocity's pointing in the direction from the origin to get to this point, but twice as big. Okay, so that would mean that the velocities tend to be pointing outwards from the z-axis. That's what I'm thinking. Yeah, possibly, and a little bit up because of the 1 here in the z. Okay, so at every point my velocity is sort of away from the z-axis but up a bit. Excellent. Cool, so things low down tend to move upwards-ish and away from the middle. Show that the curl of the velocity is 0. Okay, so curl is, just a second, curl is one of the derivatives and it tells me the swirliness around an axis, and so I would need to get that number, I would need to use the vector of the axis and dot it with something to produce a number for that speed of swirl. So the curl's going to have to be a vector, so it's going to be this one. Okay. Pretty sure the curl is a vector, but that was my reasoning for it. Okay, so the curl of the velocity is this. So, oh man, I do hate curl. So it will be d on dy of 1, which is 0, minus d on dz of this, which is 0. Good, good. And then minus d on dx of 1, which is 0, and d on dz of 2x, which is also 0. And then d on dx of 2y, which is 0, minus d on dy of 2x, which is 0. Cool. Okay. Curl is 0. Sweet. I'm pretty sure the curl of a gradient is always 0, no matter what. I reckon that's a theorem. So, I reckon it's a theorem that the curl of a gradient is always 0, no matter what.
I know we did cover the fact that the vector field is irrotational. It means it can be written as the gradient of a scalar field.
So I'm just going to repeat that. So you're saying that if the phrase irrotational, so meaning that the curl is 0, would also imply that whatever your vector is, it has to be the gradient of something. Okay, which would seem to me to say that the curl of a gradient has to be 0 or that whole thing wouldn't work. Okay, cool. So the curl of a gradient has to be 0, and if something has curl 0, then it's definitely the gradient of something. That's pretty cool. I like it. Okay. C. Give a parametric form for the elliptical path x squared plus y squared is equal to 1 and z is equal to y from 1, 0, 0 to 0, 1, 1. Okay, I need to imagine what that looks like to be able to imagine a parametric form for it. Because a parametric form will be a way of telling me what every point on that path is one at a time, based on some number which is the parameter. So at the moment, I don't have a description what every point on the path is, but if I drew it, I'd have a better idea. It's a 3D picture, which is sad. Let me just think about it. I'll get my scribble paper, which in your exam will like be blue or green or pink or something. And let's see. That's x squared plus y squared equals 1. That's a circle of radius 1. But then what we want is z to be equal to y. Z equals y is a plane. So the x squared and the y squared coordinates are related this way. And z equals y is a plane that would pass through the origin. Let me just see. Z equal to y would pass through 0, 0, 0 and 0, 1, 1, because that's where z is equal to y. So 0, 1 up here. And 0, minus 1, which would be down. Ah, okay. So we've got this plane that's sort of going through this in the middle, like that. And it goes below, underneath. Oh, okay. Yeah, not far enough. Like that. They go through each other. Ah, and then, so that explains why it's an ellipse. Because when I look down from above, it's a circle, but when I look from the side, it'll have to be stretched out to be able to fit on that. So I'm going to draw a picture of it now. So just a second. Got a circle there, and then I have the plane z equals y, which sort of looks like this. And I have an ellipse drawn there so that this point's sort of directly above that point, and this point's directly below that point. Well, in my imagination it works. Okay, cool. So that's what it looks like. And this point here is this point here is 0, minus 1, minus 1. Okay. And this is 0, 1, 0, and this is 0, negative 1, 0, I suppose. Okay. So just checking, 0, 1 for x and y would totally be on this circle, because 0 squared plus 1 squared is 1, and the z coordinate's equal to the y coordinate. Yep. Okay, that works. Okay, so that's what it looks like. Now I need a parameterization for it. Well, it seems to me that the x-coordinate and the y-coordinate being on a circle should follow the traditional parameterization for a circle, which would be cos theta sine theta.
But the points on the x-axis, you swap the x and y coordinate.
I totally have. Thank you. That's my dyslexia. I have trouble telling what positions things are in when they're left-right. Thank you. It's something I have to actually pay very close attention to when I'm doing something for other people or in an exam. Okay. You may notice when I write a word, I sometimes write one of the letters that's somewhere in the middle of the word first instead of the first letter. That's my dyslexia as well. So my dyslexia is much less severe than my twin brother's, but it's there. Okay. So I'm thinking that if I was just looking at this circle here from above, so this is from above, I'm reckoning that this would be cos theta sine theta. Because cos theta sine theta goes all the way around a circle like that. Starting here and going that way, if I use theta between 0 and 2 pi. Okay. And so that's the x and the y, and the z coordinate's the same as the y coordinate, so I reckon I can just do this. So we have cos theta, sine theta, and sine theta again because the z coordinate's equal to the y coordinate. Z equals y, and this bit comes from x squared plus y squared equals 1. Okay, cool. Sweet. So the last thing to figure out is what the actual piece of this ellipse I wanted was from 1, 0, 0 to 0, 1, 1. Oh, that's this bit here. That bit. Okay, so if I do it from above, that will be this bit from above. So it looks like I want for theta between 0 and pi on 2, because I've only gone 90 degrees. Okay. There we are. We have a parameterization. Now, I could probably do that faster if I had prepared the night before, but all circles are a sine theta, cos theta, sine theta. That's the quickest way to get them, and then you build everything else out of circles. I do have a whole revision seminar on the website specifically about making parameterizations, so it's probably worth looking. Yes?
In the solution to this question, I'm using t. Is there...
Oh, you can use whatever letter you like. It's tradition to use t for a curve. But theta was the first thing that came to mind because I was thinking circles.
Is there a reason it's not like r cos theta and r sin?
The reason it's not r cos theta and r sine theta is because the radius is 1. So if this had been a 4, I would have had like 2 cos theta and 2 sine theta. That's a very good question. All questions that are, this is different to other things, why is it different, are good questions. Okay. So that's that bit. That was part C. We're doing well. So now let's find the last bit. Use the parameterization found in part, that would be part C really. I reckon that's not, and we didn't find the parameterization in part B. Okay, just change the typo. To evaluate this line integral, the integral of C across the curve C of v dot dx, where C is the elliptical path from part C. Okay. All right. Cool. So Yeah, that makes sense that it's a dot. You can only integrate numbers, and v is a vector, and dx is a vector as well. So you have to dot them to get a number to integrate. So my x, or I'm going to need to figure out what dx is first. Sorry, I'm just going to rub that out because that was a waste of time, sorry. So, just a second. My x was cos theta, sine theta. And so my dx will be the derivative of that with respect to theta times d theta. So derivative of cos is sine theta, the derivative of sine is cos theta, the derivative of sine is cos theta, and that will be a dt, d theta. Traditionally it's a dt, but this will do. Okay. Does that bother anyone, the way that I've written that? Good, because I think of all derivatives like that. It's d something equals thing times d other thing. So the movement, this is the current x position. The change in the x position will be the derivative times the change in the theta. Okay, so now I need to know what v, so now I can do it. Oh crap, no I don't. Sorry. What was the v? 2x, 2y, 1, which is 2 cos theta, 2 sine theta, 1. So I've taken the x position and I've subbed it into the v coordinates. Be very careful when you do this because it's extremely common for people to sub this into there and just get it wrong. Okay? So my v dot dx is now minus 2 sine theta cos theta plus 2 cos theta sine theta plus cos theta. Oh, that's convenient. All right, cos theta. Okay, so the integral across C of v dot dx will be the integral from theta equals 0 to theta equals pi on 2 of cos theta d theta. Sorry, that v dot dx, the dx has a d theta in it, so there needs to be a d theta when I do the dot product, which is 1, because I happen to know that. Do you want me? Let me do the long way. Sine theta from 0 to pi on 2. The integral of cos is plus sine, from 0 to pi on 2. Sine of pi on 2 is 1, which is 1. Okay, sine of cos, sine of pi on 2 is 1, sine of 0 is 0, it's just worth knowing for future reference that you know how sine and cos are made out of all these little bits that are this shape? And there's like a bit here, and then there's a bit here, and then there's a bit here, and sine is the same, but it's moved over a bit. The area of this bit is 1. So useful to know for future reference that the integral of cos from 0 to pi on 2 is 1. The integral of sine from 0 to pi on 2 is 1. And if you have a pi on 2 zone like that, that little looks like a piece of a circle but isn't. That little bit, the area is 1. And a lot of maths lecturers sort of just use that fact blithely without actually calculating integrals at all. So I'm pretty sure you're allowed to do that too. Okay. Now this is the bit you really wanted to know. Okay, use the scalar velocity potential number 1, which was this thing here. This thing just here, okay. To evaluate the line integral number 2, which is this thing here, and hence check your result. Okay, so we're supposed to do this integral a different way and get the answer 1 again. Okay, cool. Well, let me just write it down. So we're saying that this v is actually del f. It's just a gradient. Okay, so the gradients are kind of derivative. and an integral of a derivative should be the original function, as long as that function is irrotational. So as long as the del f, just as long as the del f. The integral of a del f should just be the difference in f from the beginning to the end. So this should be f at the start, which was, what was the start? 0, 1, 0, 0? Oh yeah, 1, 0, 0. No, f at the end minus f at the beginning. Yeah. Pretty sure that's the deal. Just let me have a check at the little thing that was at the back of the exam. Of course not. It's not there. We just have to know that one. Okay. So f of 0, 1, 1 is 0 squared. So that's the formula there. X squared plus y squared plus z is 0 squared plus 1 squared plus 1 minus 1 squared plus 0 squared plus 0. And we get 2 minus 1, which is 1. Okay, it works. So it's just, this is worth noting. When we did integrals back in first year, and you did the integral of a derivative, it came out to be the original. Well, when you integrate a function, you go, okay, so I'll just find the antiderivative and I'll do sub in the bottom, the top, and minus what I get when I sub in the bottom. That's what I'm doing here. I'm doing a curve that goes in space from one place to another, and the thing I'm integrating is already a derivative, and so I will just get the original function and the difference between the end minus the beginning. Yeah, so yeah, integral across this curve of a derivative will be the original function here minus the original function here. So the big trick, I think, is supposed to be that if you have a function which happens to be irrotational, the quickest way to find an integral of it across a path is to first figure out what function it's the gradient of, and then you can just sub it in. Okay? Does that answer what you wanted to answer? Okay. So this is sort of like the secret integral theorem. So there's 3 integral theorems in the course, which are like divergence, Stokes, and Green's, but there's a secret 4th integral theorem, which is this one. This thing here. That the integral of a gradient is the difference between the function at the two ends of the curve. Cool. All right. Well, maybe I'll go looking in here for another question to do that's about these things. Did quite well on the space using in that one. I didn't actually use all that much extra space on top of what they gave me. I'm getting better. Or maybe it's just a coincidence. I might just skip to question 5. Let me just look at question 4. Do you know what? These are all good things to do. I just gonna do it. Consider the region R, which has the equation, well, there are inequalities, I suppose, but these are the rules. X minus 1 is less than or equal to y, which is less than or equal to 1 minus x. And x is between 0 and 1. Sketch the region. Okay. Well, that bit would be x minus 1 is less than or equal to y, so y is greater than or equal to x minus 1. So y equals x would be here, y equals x minus 1 would be here. So that's x minus 1 is equal to y there. And, all right. Just let me on the side of the page do a quick little version of this. So we want y to be greater than x minus 1, which means we want this bit above it. And just let me check a point. When I have 0, 0, 0 minus 1 is less than 0. Okay, so 0, 0 is on the correct side. So I'm just going to cross out the bit I don't want. I don't want that bit. And then y is less than or equal to 1 minus x. So minus x would go this way. 1 minus x would be there. So and y being less than that would be below it, so I don't want this bit up here. And then I want x to be greater than 0, which would be none of the negative x's. And I want x to be less than 1. All the x's in there are less than 1 already. So the bit I want is this bit here. I find it easier to cross out the bit I don't want. That leaves me the bit I do want. But you don't want to give them there. Like, I'd normally do that on the scribble paper. This looks prettier. Okay, cool. I can do that. The Maths 1As did that in this semester's exam when they were doing convex sets, so I'm good at that. Really good at first year. Use Green's, I do 1A twice a year, so really good at that. Use Green's theorem to evaluate that integral. Okay, where C is the boundary of R traversed in the anti-clockwise sense. So C is round there. Okay, and F is that. I'm just going to write that as a vector for myself because I hate it with the I and the J. Okay, cool. So Green's theorem is a way of connecting a single integral around a curve with a double integral across a region. Because the theorems are all about integrals going one up or one down. So I'm at a single integral, and Green's theorem is either one up or one down from there. So I know it's one up from there. It's a double integral. And I'll just check. Green's theorem says that the double integral of dv on dx minus du on dy, dx dy, is the integral around a curve of u x dy dx plus v x y dy. Right, so this thing here is totally u v dot dx dy. I'm just going to write that down. So the integral around a curve of f dot dx is the integral around the curve of x squared plus y dot dx dy, which is exactly xy dx plus x squared plus y dy. Okay. So according to Green's theorem, I've got a u and a v, a u dx and a v dy. That's what I've got here. And so I should be able to turn that into a double integral of this thing. Okay. So that's a double integral across the region of this on dv on dx, which is 2x, minus du on dy, which is x. I just might put a little bit of working on the side just to make sure I've got that right. U is equal to xy, v is x squared plus y. So du on dy is x, and dv on dx is 2x. Okay. And it's dv on dx minus du on dy. Yep. Okay. Sweet. Sweet. Okay. So now I have to do this double integral across the region of x, dx dy. Okay. That means I'm going to have to parameterize my region. I mean, I don't have to parameterize it, but I need to figure out how to tell what all the x's and y's are in that region. So let me just go have a look at my region. I might redraw my region bigger. Okay, so that's my region. So when I do integrals, if I'm going to do integral dx dy, then I could do it dy dx if I wanted, it doesn't really matter. But I need to, if it looks to me like the quickest way to pick a point in this curve would be to pick the correct x-coordinate, and then once I pick the correct x-coordinate, to go up and down across on a line that would choose the y-coordinate within the possibilities given that x-coordinate. Okay, so I'm going to choose x between 0 and 1, and then given that x, I'm going to choose y between, I suppose it's between, what was this? This was y equals 1 minus x, and this one was y equals x minus 1. So between x minus 1 and 1 minus x. That's, once I've chosen the x, I can go between here and here. Okay? So that means that the integral I was thinking of, which was this, in an exam I probably wouldn't repeat this bit because the examiner can read it on the opposite page, but if you've gone to a different page, it's probably worth repeating what you just said so it's not so hard for them to read it. But yeah, I'm on a new page, so I'm just repeating it. Okay, so I'm going to choose my x first, which means I'm going to go dx first, from x equals 0 to x equals 1. And then I'm going to go from y equals 1 minus x minus 1 to y equals x, 1 minus x. And that's going to happen next. So I chose the x on the outside, and then I chose the y, and the function I have is x. Sweet. Okay. So x doesn't involve a y, so when I integrate it, I'm going to get... Actually, I reckon I can... No, it's going to turn to crap. It's all right. I can pull the x out the front here and just do the integral of y. And I thought that I might be able to pull that whole integral outside the other one, but that integral's got x's in it, so it's not going to work. Okay, so the integral of x with respect to y would be x times y. So this bit here has become this bit here. So you will notice I am being extremely explicit that this one is about the x's and this one is about the y's. If I don't do that, because there's x's here and here and here and here, it gets really confusing. So I'm saying this one is y equals to y equals, this one's y equals to y equals. Otherwise I'll end up subbing it into the wrong bit. So I sub in y equals 1 minus x, and then y equals x minus 1, and subtract them. So what have we got? We've both got an x. Let me just expand it out. Got that right? X minus x squared plus it. Okay. That was unexpected. So now everything's x's. I can probably remove this x equals thing here. So that becomes the 2x, the 2 will still be there. I'll go up to an x squared, but I'll divide by the 2. The minus 2 will still be there. I'll go up to x cubed, and I'll divide by the 3. And so I've got 1 minus 2/3 of 1 cubed minus 0 minus 0. Okay? Which is 1 minus 2/3, which is a third. Sweet. Right. So an important key to realise here is that they said to use Green's theorem to do this. It should technically be possible to calculate this integral directly by doing a path here and a path here and a path here and adding them all up. And the lecturer, it probably has a part of their mark scheme to say how many marks you'll get if you do that, which would be not the whole number of marks. because you haven't done what they've asked. So using Green's theorem makes it a little easier because it's easier to integrate across a region like this than it is to do 3 separate path integrals. Yeah. But if you, unlike me, have half an hour left in your exam, do it the other way and check it comes out to the same answer, and then you'll know you're right. But I have never been in that situation, so yeah. Except for one very, very nice exam where I could do everything except this one question, and I kept having to come back to it. So, okay, cool. Is that the end of question 4? I think it is. So what have we done so far in this exam? So far in this exam, we've had a potential, so we've done a gradient, and we've done Green's theorem. So I would expect there to be at least, if not both, but at least one of the Gauss's divergence theorem or Stokes's theorem, at least one of them, because I can bet that they really want me to do a surface integral somewhere in this exam. So let's just see if it's here. There it is. Looks like we're going to do Gauss because we're doing a region, or we're doing a volume. All right. Show that the volume of a region enclosed by a surface S is the volume, which is equal to a third of the double integral around the closed surface. Yeah, around the closed surface S of r dot n hat ds, where n hat is the unit normal pointing out of the region, and r is x, y, z. Okay. Aha. Well, I can think of 2 ways to do this. I could write down what I think the volume ought to be. So the volume ought to be the triple integral of just dv across the volume, and work backwards from there and try and turn it into this, or start with this and try and turn it into the volume integral. Probably easier to start here because this is more complicated. It's usually easier to try and make more complicated things simpler. 2 marks apparently, and fitting in this space, okay? Now, I won't say volume equals at the front because I don't technically know it's equal to the volume yet. I'm just underlining them because they're in bold here. So I don't know it's equal to the volume yet, so I can't say volume equals until I find out that it happens to be the volume. So I'm trying to start here and end up at equals volume at the end. Okay. So, okay. Well, one of the theorems ought to help. Oh, here's one. Gauss's theorem says that the integral across a closed surface of f dot n hat ds is the triple integral across the volume of the divergence of f dot dv. So we can use that. So this should be 1/3 of the triple integral across the volume delta dot r dv, where is the region. Because they haven't told me what the region is called, they've only told me what the surface enclosed by it is. So I need to tell them what this letter stands for. Okay, and the divergence of R would be, I should probably just figure that out. I might, for the purposes of this, go over here and say that del dot r would be the derivative of the first coordinate with respect to x, which would be 1, plus the derivative of the second coordinate with respect to y, which is 1, plus the derivative of the third coordinate with respect to z, which is 1, which is 3. Okay. That. And I could bring the 3 out. And so I just get that, which is the volume. Because when you integrate a little piece of volume across a volume space, you get the volume of the space. Essentially what we're doing is we're adding up 1 times the volume for every piece of volume, and so we end up with a total volume. Like as you move across the volume, you accumulate 1 piece of volume for each piece of volume, and so you get the total volume at the end, as opposed to accumulating 1 piece of pressure for each piece of volume, in which case you get something else. Okay, cool. That's good. So technically we sort of used this divergence theorem, but we didn't do anything fancy like actually using a crazy function. Consider the closed surface S parameterized by this, okay, where u goes from 0 to 2 pi, v goes from minus pi and 2 to plus pi and 2, and a, b, and c are positive constants. Okay. Give the Cartesian equation for S and sketch the surface. So I'm guessing that they are thinking that by finding the Cartesian equation, I should be able to recognize what the surface is. And a Cartesian equation doesn't tell you what any of the points on the surface are. It tells you a single equation in x, y, and z, or however many variables there are, that if it satisfies that equation, if a coordinate satisfies that equation, then it's on the surface. So that's what I'm going to want to do. I'm going to want to somehow turn this into something involving x and y and z, but no u's and v's. Okay? Now I can guess what this is actually just from this information here already. So if I look at this bit, there's a cos v and there's an a cos u, b sine u. So if it was just cos u sine u, there'd be like a circle of radius cos v. So given every v, there's a circle there, only it's not a circle, it's wider in one direction than the other, like the a and b are different numbers, so that makes an ellipse. So at every v, there is an ellipse with radius cos v, not really sure what that does, and then the height is c sine v. Okay, so this surface is made of ellipses at different heights. I don't know exactly how they get bigger and smaller at those different heights yet, but I know it's made of ellipses. So it might be some sort of cylinder or some sort of cone or maybe a ball or maybe a bowl. Don't really know yet, but that's what I expect it to be. So let's see if we can figure out what it is. So let's see. X is a cos u cos v. Y is a b sine u cos v. And z is c sine b. Gosh. It occurs to me that the quickest way to get rid of coses and sines is to square them and add them together. So x squared is a squared cos u squared cos v squared. Y squared is b squared sine u squared cos v squared, and z squared is c squared sine v squared. Okay, so I've got something times cos u here. Oh crap. If these were the same, if these a and b weren't here, then I'd have something times cos u squared and the same things times sine u squared. So the cos squared plus sine squared would become a 1. So I'm going to need to divide out the a squareds and the b squareds to make this work. So x squared on a squared is cos u squared cos v squared. Y squared on b squared is sine u squared cos v squared which together means that x squared on a squared plus y squared on b squared is cos squared times this thing, sine squared times this thing, which when I add them together will be 1 times this thing, so that will just be cos v squared. Okay. Yeah, the cos v squared plus the sine v squared would be 1. So if I do the z squared minus over c squared, there's enough room to put that there. Z squared over c squared is just sine v squared. And so therefore, x squared on a squared plus y squared on b squared plus z squared on c squared is cos squared plus sine squared, which is 1. All right, there it is. That's my Cartesian equation, which is an ellipsoid with radius a in the x direction, b in the y direction, and z and c in the z direction. That's interesting. This course is going to have to be different next year because ellipsoids aren't in Maths 1B anymore, in the new Maths 1B. That's going to be fun. Okay. So I was right about the ellipses. So this is, if it was x squared plus y squared plus z squared, that would be a sphere, same as how x squared plus y squared equals 1 is a circle. So that dividing by those different things gives you different radiuses in different directions. Okay. So this is an ellipsoid. It goes from a to minus a on the x-axis, from b to minus b on the y-axis, and from c to minus c on the z-axis. There you go. So you saw how I drew that. I drew an ellipse in the zx and an ellipse in the zy, and then I sort of filled out the edge. Technically there's one here too. Yeah, no, just getting crap now. So draw two of the ellipses and then fill out the edge. Okay. I wonder if we've covered the whole surface. Let me just check. If the v goes from minus pi on 2 to plus pi on 2, then sine v will cover everything from minus 1 to 1. And so therefore c sine v will cover everything from minus c to plus c. Okay, so we have covered everything upwards. And if this cos u sine u goes everything from 0 to 2 pi, we've gone all the way around every ellipse at every height. Okay, we have covered the whole surface. But if it had only gone from like 0 to pi on 2, we would only have the top half. So just thought it was worth checking. It wouldn't make any sense based on this first one for it to be something that had a hole, like a gap, because this integrals of this integrals here of a closed surface. So if I'm going to relate back to question A, I would expect it to be a closed surface, but I just wanted to check. Okay. What's the next question? Where's the rest of this? Oh, okay. That's sad. Find the normal. I can do that. Okay, so R was A cos U cos V, B sin U cos V, C sin V. So R sub U, okay, so the A is a constant, it'll still be there. The cos V is a constant, it will still be there. It's multiplied on. Cos U will become a minus sin U. B is a constant, it will still be multiplied on, still be multiplied on. The cos V is a constant, it will still be multiplied on. The sin U will become a cos U. And this doesn't involve u at all, so that's a 0. V, the a cos u will still be there because it's multiplied on. The derivative of cos is minus sine. The b sine u will still be there. That'll be minus sine. And the derivative of sine is cos. Okay, so they're my two derivatives. Really? Gosh, when did that happen? Wow, okay. It's not nearly as exhausting as the last revision seminar I did, but to be honest, that one was in the afternoon after having done one in the morning, so that explains why I'm not so tired. Plus the exam is telling me what to do. I don't have to make decisions, so that makes it easier. Okay, so I cross them. So this one will be b cos u cos v squared. Oh, and then there's a c as well. And that bit's 0. Okay. And this one will be minus, let's see, this times this will be ac sine u cos v squared. And this one will be, oh crap, run out of space. So what have we got? Those two, so ab sine u squared cos v sine v minus, actually plus, because there's already a minus there, ab cos u squared cos v sine v as well. Ah, look at that. Look, all of this is the same, and there's a sine squared and a cos squared, so that's going to be a 1. So b c cos u cos v squared ac sine u cos v squared, comma ab cos v sine v. Okay, it's not pretty, but there it is. Hopefully when I dot it with something later, everything will cancel out. So that thing happened again where we noticed a sine squared plus a cos squared times other crap, and those things added together so that we were just left with the other crap. Seems like a thing that we should get used to. Find the volume of the region enclosed by S by evaluating the surface integral in part 3. Okay. So the volume, according to part A, should be 1/3 of this surface integral of r dot n hat ds, which should be 1/3. Okay, so n hat ds should be the same as capital N times du dv. Pretty sure. And so what do we get? What's r? Oh, I need to figure out what that is separately, just a second. R dot n is x, y, z dot with n, and x is a cos u cos v, b sine u cos v, c sine v dot n. Right, so somehow I need to dot these things together. Wow, those things need to be dotted together. Just leave that there for a moment. Zoom out a little bit, I might be able to fit it all on the screen at once. Okay. Do I have the space? Okay, so this times that would be ABC cos u squared cos v cubed. Yeah. Okay, sure. And this times this would be ABC sin u squared cos v cubed. Nice. And this dot this would be ABC, good, cos u times sin v squared. Okay, really do need more space now. I was hoping it would all work out, but all in one go, but no. So what have we got? Those bits are the same, and this cos squared plus sin squared would make a 1, so we get ABC cos v cubed plus ABC cos u sin v squared. But just a second, cos v cubed, yeah, look at that. This is a cos v, isn't it? Look, cos v squared, sin v squared, and the other bit's the same. And so we get ABC cos v. Ah, brilliant. Yes! And so therefore my volume is actually the integral of this. ABC. So I just have to figure out what the u's and the v's do. So u went from what? 0 to 2 pi. Oh, the v's on the outside. I should do the v second then. So the v went from minus pi on 2 to plus pi on 2. The u went from 0 to 2 pi. And I have ABC cos v du dv. Okay. Now that I can do. I don't have to actually do any of this now, because this doesn't involve a u, so I can bring it out the front. So I took this integral, and that bit doesn't, that bit doesn't involve v, so I can take it out the front. And the integral from 0 to 2 pi of du is just 2 pi, because I'm going to have u from 0 to 2 pi. Yes. So ABC cos v times 2 pi. Okay. Doing well. Okay. So you've got 2 pi ABC on 3. So just so you know, this bit here became that 2 pi, just so that we don't lose track of what happened. And, well, let's see, cos from minus pi on 2 to pi on 2 is 2, because this area is 1 and this area is 1. Because cos does this, right? All right, so this is 2 pi ABC on 3 times 2, which is 4 pi on 3 times ABC. Done. Yay! So just also for future reference, this bit here is calculated with this picture. And that's what it should be. So In my head, I know that if it was a sphere, the volume would be 4 pi on 3 times r cubed. But because it has 3 different radiuses in 3 different directions, it's the 3 different radiuses times together. So cool. That's what the volume should be. That's good. This is nice. I should do some complex stuff to just do the last thing that I was asked to do. So I was actually sent by someone a picture of something from one of the tutes, which had a whole lot of different little integrals, and I may or may not do that one. I'm just going to check if there's some fun little integrals to do here. There, I might actually pull the one out of the tutorial that I was sent, or not, I don't know. What happens in tutorials? Does someone do basically this? Okay, do they get through everything? Okay, so I'm... And by get through, if they get through everything, that means that it's not nearly as decently covered as if... Yeah, so, okay. Well, those are my thoughts on tutorials. Okay. I'm just going to look up the questions that I was sent. Revision seminar requests. Okay. I'm just going to go through some reasoning. So this is not the exam. So let's see. I'm just going to go through these examples and see what we have. What the hell is going on there? It says on my screen that it's not paused. Just a sec. Right. I think I confused it by pressing pause twice and then pressing resume, but not pressing resume twice. There should be one button that when you press it, it pauses, and when you press it again, anyway. Don't get me started on lecture recording systems. This one is not worse than the old one. Anyway. Okay, so we have the integral of 3 over z plus 1 dz, where c is the circle, the length of z plus 1 is 2. Okay, so well, let me see if I've got this right. So I'm pretty sure that if your function has a hole in it that's inside the curve that you're integrating around, then you will need to do something special there. There'll be like some sort of residue thing, and you'll multiply it by 2 pi I. But if your function doesn't have a hole in it inside that circle, then the integral will be 0. So I know where the hole is. The hole is where z is equal to -1. So we have, now what's the word for that? A pole? Singularity maybe? Sorry? What? Either, okay. I thought you said fiber, and I'm going, what? Okay, pole. So singularity, the difference is that that a singularity isn't a pole if you've got like infinitely many negative power bits, I think. So like e to the minus z no, not e to the minus, yeah, something like that. So this is definitely a pole. So a pole at z equals -1, because it's when the denominator is 0, basically. Okay, and we should draw this circle. So this circle, that would be the same as z minus -1. Okay, so this is saying that it's all the z's whose distance between z and the number -1 is 2. So it's a circle of radius 2 with centre -1. So here we are at -1, and it's a circle of radius 2. That's what C is, which squarely contains my pole, and so therefore it, okay. So I'm going to have to figure out the residue of this function. So what's the deal? You ignore the bit that has the z plus 1 and then sub -1 into that function? I think that's how it's done. Let's just see. If f has a pole of that. So we have a pole of order 1. Oh, here's a simple pole. Okay, so we multiply by the annoying bit, which makes it go away, and then we sub in z equals the pole into the function. Okay, cool. So the residue of 3 on z plus 1 when z equals -1 is 3. If that had been a 3z, then this would have been a 3 times -1. If that had been a 3z squared, then this would have been a 3 times -1 squared. You would sub the -1 into this part here. Which makes me want to do this with another function, so I just want to check something in a second. And so therefore, the integral around this is 3 times 2 pi I, which is 6 pi I. Okay, so I think this contains within it everything that we probably need to know in order to do these kinds of questions. I'm going to create another example here that's related to this one. It's one of my classic ways of trying to figure out how things work, is to go, well, what would happen if this was different, and then see if I could figure it out. So I'm just going to do the same example and change one thing at a time. Yep. So good, that's the first thing to change. Let's do that first. EG, same. Yep. Same but clockwise. Then the integral would be -6 pi I. Yep. Good. And the reason that works is that if you did this path integral properly by parameterizing the curve and doing the multiplication and adding it all up, then going in the opposite direction, all of your derivative of the curve would just be minus what it was before, and everything else would be the same, and so you just get a minus out the front. Okay, good. That was an excellent what if. So this next one I've done the same function. And it's the same direction. Then I would need to, and I had the same problem. Okay, I've still got the pole inside the circle. It's still the same. And so I'm still going to have to figure out the residue. So it's going to be easier to say this. Damn it. Let's just give this bit on the top a name. (3z plus 5). And then we're going to say that the residue of 3z plus 5 on z plus 1 when z equals -1 is f, g, damn it, there was no point doing that. It's just 3 times -1 plus 5. Okay? I sub this number into the bit on the top. Equals 2. And therefore the integral of curve of 3z plus 5 over z plus 1 dz is 2 times 2 pi I. Okay, and I'm building up to something. What about this one? Oh, actually, can I just change this here z to not a z, to a z plus 3? Okay. Okay. So we have almost the same. So let's just see. So I have pole at z equals -3 and z equals -1. My circle, oh crap. I'm going to change it again. That's going to be an 8. Because I don't have to rub it out to change it to an 8. Okay. The pole ended up being right on the edge of my curve, and then there is no integral. So if your curve passes through a pole, the integral doesn't exist. Just need to point that out. But I don't want to go there. I wanted one over here at -8 and one at -1. They're my two poles. And only one of them is inside the curve. And so I don't need to worry about this one because it's not inside the curve. Only z equals -1 is inside C. Okay. So I'm going to need the residue of this function when z is -1. I might give the function a name now. So to figure out the residue of this function when z is -1, I'm going to need to remove the part that has the z plus 1 on the bottom. So I need to remove the part that has z plus 1 on the bottom. And that's why they talk about it as a z plus 1, because you multiplied it by that. And then I'm going to need to sub in z equals -1 into that to figure out what the residue is. So when z equals -1, this is equal to 3 times -1 plus 5 over -1 plus 8, which is, 2/7. And therefore the residue of f when z is -1 is 2/7. And therefore the integral of f around this curve is 2/7 times 2 pi I. So the point I wanted to make is that if you have two poles on the bottom, when you do the residue of one, the bit that's on the bottom of you need to leave the other part on the bottom still when you calculate it. That's just an important point, because when I first learned this, I didn't do that and everything was wrong. So I just thought I'd point it out. Okay, and I guess another what would happen is what if there were two poles inside there? So I'll go back to the one that I almost did just before. same curve, but I've just changed the z. The z plus 8 is now a z. So now I have poles at z equals 0 and z equals -1. So when I draw my curve, I've got two poles. I don't need the z's. And so all that means is I'll just figure out the residues of both of them and add them up and then multiply by 2 pi I. So let's just see. So they're both okay. So the residue of f of z when z is 0 will be what I get when I take the function without the part that makes the bottom equal to 0 when z is 0, and I sub into it z equals 0. I couldn't remember this notation until just now. That's how to do a notation of function, and then you sub this in. So you go function, then like this little ceiling thing, and then you sub it in. And so you've got 3 times 0 plus 5 over 0 plus 1, which is 5. And the residue of f of z when z equals -1 is... So this time I've removed the part that makes it bad when z is equal to -1. And then I'll get... which is -2. So therefore, the integral around the curve of f of z dz will be 2 pi I times what I get when I add these together, which coincidentally is the same as the first answer we had, but that's a coincidence. So the only other thing I can think of is what if it wasn't a straight up thing and it had a squared or a cubed or something in it. That's my other what if. So yeah, that'll work. Z to the 4 plus 2. Let's go. And let's change everything. Let's change it all. So, there we go. Whole new question, completely different. It's probably a bad move. I should only have changed one thing, but anyway. It's got the same pole. Okay. So let's actually figure out our curve. So the center is I this time, and the radius is 5. So it goes down to -4i, goes up to 6i. Whoa. Hint for drawing circles. Draw the circle first and then label it. And my pole is at -1, which is totally inside this circle. That's why I made the radius 5, just to be sure. So, cool. So the pole is order 3 because it's z plus 1 cubed. That's why it's order 3. And so we're going to have to use the fancy formula in the notes So this says I'm going to need to do the second derivative, so one derivative less than the number we have, of my function but with the annoying bit removed. And then sub in z equals 0, z equals the point I'm interested in, and divide by factorial. Okay, let's do it. I think we need a name for this. So if I look at my function and I remove the annoying bit, that will leave me with z to the 4 plus 2. So I'm going to call this g. Okay, and then I'm going to need the second derivative of that bit. So just before I write that, I'm going to go, it's a third order pole. I need the second derivative. Okay, so g dash z is 4z cubed, g double dash z is 12z squared. Okay, and then I'm going to need to sub in or do the limit of z goes to I, conveniently. So the limit as z goes to the pole of g double dash z is 12i squared, which is minus 12, because I squared is negative 1. And so therefore, the residue as z equals negative 1 of my original function, I should have given that a name too, is this divided by 2 factorial, because I haven't done that part yet. It's negative 6. Right. And so therefore the integral of z to the 4 plus 2 over z plus 1 cubed dz, damn it, is minus 6 times 2 pi I. Just minus 12 pi I. I think that's the process. Find the part that doesn't have the annoying bit that's involved, differentiate it as many times, one less times than the power that was there. Yes?
Why did you sub in I when I is just the center of the circle?
Oh, for the sake of Frel, David. Thank you. It's not I at all, is it? Thank you. Negative 1. Yeah, because the pole is negative 1. That's the pole there. Right. Next time I do this, I will mark the pole extremely clearly so I don't think it's the center of the circle that I'm interested in. Okay. But that's okay. Everything's just changed the minus sign. Okay. Well done. I did it right here. I should have chosen something with the pole of I. That would have been nice. That's my understanding of the whole thing, except for having a big double bluff and it doesn't have any poles inside it at all, and then the answer is just 0. Whoa, wow. Any questions or thoughts about integrals around closed curves or anything in anywhere else? About this or anything else? Because I'll keep talking, maybe for another quarter of an hour. Wow, the one in the book is this exam is awful, isn't it? Gotta do that one. Consider the complex contour integral that, where C is the circle z minus 1 equals 2 traversing the anticlockwise direction, is sketch the curve C and the poles of that in the complex plane. Oh, bugger. All right. So the poles are going to be wherever that's 0. And so we're going to get z equals 0, or z cubed is 8. Oh, and one of the cube roots of 8 is 2, and the other 2 will be imaginary, well, not real. So I'm going to have to write that in polar form. So it's currently 8e to the 0, that's definitely true, plus some multiple of 2 pi I. And so then when I do the cube root, I'll do the cube root of 8, which is 2, and the cube root of this, which will be that divided by 3. Okay. So that's the trick for doing roots of complex numbers. Take whatever, you need to write the number in polar form. If it's a real number, the polar form is e to the 0. And then you need to make sure you cover all the possible polar forms of that number, like that. And the k there, every time I get to a multiple of 3, I'll just be adding another 2 pi, which won't make a difference to the answer. And so therefore, there's only 3 answers. So I can go 2. We knew that one was there. That's when k is 0. That's when k is 1. And I might do the negative one. That's when k is negative 1. And those are 3 different answers, and I know there's only going to be 3. I could have done 4 pi on 3 if I wanted. It doesn't really matter. As long as you get 3 different consecutive k's, you can do get all the answers. Okay. Sorry? Yeah, I totally do. Well done. Yes, I subbed in k equals 2, k equals 1, and magically this 2 disappeared. Yeah. Okay. So what have we got? So we have 2, which is here. And this one is 2, but it's 2 pi on 3, so 120 degrees around the circle from here. So I'm just going to draw this circle. And it'll be over there. And then this one will be over here, the other direction. So they're my poles. I can probably figure out exactly what those points are, but they just said to sketch it. They didn't ask me to do it any particular way. And also there's the pole of 0. Okay, so they're my poles. And now I just need to sketch what C is. Let's see. C is the circle of radius 2 centered at 1. So 1, 2 there, 1, 2 there. Cool, doesn't even include my crazy poles anyway, so that's okay. Neat.
How do you determine that? So,
C is a circle, center 1, radius 2, because it's all the z's where the distance between z and the number 1 is 2.
and that comes from just like the question of the...
Yeah, they told me this here. Yeah, they told me what C was, so that's all right. And in this, for this function, you would really need to know what C was, because it's got 4 poles that you could contain. Yeah. All right. So only z equals 0 and z equals 2 are inside the curve. so that's good. We can use them now. So we're going to need to find the residues of those two poles, and those two poles are of different, have different orders, or is it degree? Orders, different orders, so we're going to have to do it differently. So for the pole z equals 0, I'm going to need the function without the z equals 0 bit. And I'm going to need to differentiate that once, because of the pole is 2, order 2. So order 2, differentiate once and divide by 1 factorial. So the old one was the one in the other example was order 3. I differentiated twice and divided by 2 factorial. These two numbers are always 1 less than that number. I've just put a 0 here because I want to have a function for the other one as well. So I thought I'd call this one G0 and the other one G2. There's no particular reason that you have to do that. It just appealed to me today. So, oh bloody hell. The derivative of the bottom is 3z squared. Keep the top. No, you keep the bottom. Keep the bottom. Differentiate the top. Minus. Keep the top. Differentiate the bottom. Divided by the bottom squared. Wow. Yay, quotient rule. So we'll sub in 0, which would be minus 8 times 1 minus 1 times 3 times 0 over 0 minus 8 squared. Okay, so minus 8 divided by minus 8 squared would be minus 8. Beautiful. No, minus an eighth. Just a second. Minus 8 divided by 64. Right, okay. And so the residue of my original function, which I should have called f, when z is equal to 0, is this number divided by 1 factorial, which is minus an eighth. Okay, that's good. So now let's do the pole z equals 2. Oh crap, I'm going to have to get rid of the bit that just has the z equals 2 in it. The z minus 2. Makes me annoyed. So I'm going to have to factorize out the z minus 2. Yep.
Wouldn't it be easier to just run with the whole thing and then...
Times by z minus 2?
Yeah.
Except if when you sub things in, you're going to get 0 over 0.
Which you can use the Morse theorem for.
Oh, because it's a limit.
Yeah.
You mean L'Hopital.
Sorry.
You picked a theorem that went with complex numbers. Well done. That's important. Oh, sure. We could do that. I know how to factorize this, but so I'm going to do that too. I'll do an OR. So when you factorize a cube minus a cube, the difference of two cubes, when you factorize a difference of two cubes, you get the difference of the originals and thing squared, thing times thing, and the other thing squared. So just so you know, a minus b times a squared plus ab plus b squared is a cubed minus b cubed. In case you're wondering. Okay. So the bit I want is the bit that doesn't have that z minus 2. And so since it's a simple pole, since it's order 1, I don't have to differentiate at all. Order 1, I just need to put in the number. What the hell? We've got a 4, and we've got a 4 plus another 4 plus another 4. So 3 times 4. So 1 over 16. Yay. And so therefore, the residue as z equals 2 of my original function is 1 over 16 divided by 0 factorial technically, but that thing there. No, 16, yep, 16. Yep. And so the integral of my original function around this curve dz is 2 pi I times the sum of the residues. And an eighth is 2/16. So 1/16 minus 2/16 is negative 1/16. And so I get minus an eighth of pi I. That's what I get. So I do want to try your method of figuring out the residue there, because that sounds cool, especially if you had something that you really didn't know how to factorize. Okay, so you're saying that I had my original f of z, which was what? Z plus 1 over z squared, z cubed minus 8, and then z minus 2 times f of z was z plus 1 over z. Like that. And then you do the limit of that as z goes to 2. And you're telling me that I'm supposed to do L'Hopital's rule because the top and the bottom are both 0? Okay. So the top and the bottom are both 0. I could do L'Hopital's rule, which would require me to differentiate the top and the bottom. Okay. Where am I here? So L'Hopital would give me... So I could expand it out, or I could go product rule on it, right? So 1 times z minus 2 plus 1 times z plus 1 times 1. And the bottom I could go product rule as well. 3z squared, keep the z cubed. Sorry, that's a z squared, isn't it? Damn it. 2z, z cubed minus 8. Plus z squared times 3z squared. And then I could sub 2 into that. Cool. So that would be 1 times 0 plus 3 times 1 over 2 times 2 times 0 plus 4 times 3 times 4, which is what we had before. Nice. Cool. That's fun. And so I didn't have to actually expand it out at any point because I was subbing in z equals 2 anyway, and most of it cancels out because z cubed minus 8 is 0 anyway. That's really nice. I like this. But I also happen to like factorising cubics, so, you know, do whatever appeals to you at the time. The first thing you think of that works is the thing you do in an exam. So if you do think of two things simultaneously, you choose the quickest one, right, in an exam. Okay. I'm glad I did that one. Oh, I haven't finished yet. Yes, I did the integral back there. Okay, good. This was just an alternative way of getting to part of that calculation. All right. Well, burning questions? Or if you have any others that you don't feel like airing in front of on a recording, the Maths Learning Centre is open 10 a.m. to 4 p.m. till the end of the exams, in particular until whenever your exam is. And feel free to come and chat. Either me or Nicholas will be there. Yeah, thank you very much. I wish you clear thinking and good memory and calm nerves.